All right, here we go. Cole, how's it coming? Good. All right, you did number 4. All right, number 4. Local minimum at 1 comma e. So if you have to train yourself now that we have a second derivative test, you have to train your mind to say, am I doing the first derivative test for maxes and mins and f is increasing and decreasing? Or am I doing the second derivative test for concave up, concave down for f, and where the concavity changes is called a point of inflection. So, ooh, it sounds like a SAT question. A critical point is to the first derivative as a possible point of inflection is to the second derivative test, right? Do you agree? In this one, critical point, to become a max or a min in extrema, to become extreme, f prime has to change positive, negative, or negative, positive, right? To have a point of inflection, f double prime has to change sign. And so when I say to justify, we practiced justifying maxes and mins yesterday. Remember that? F has a local maximum at x equals c because f prime changed from positive to negative there. Remember that? How about justifying a point of inflection? F has a point of inflection at x equals k because f double prime changed sign there. That's all you need for a point of inflection is a sign change in f double prime. Doesn't matter how it changes. Either way, it's a point of inflection. In the first derivative, it mattered how f prime changed. One was a max, one was a min. Right? Good job. All right. Let's see. Cole did a product rule. Yes? Mm-hmm. First times derivative of the second, and the derivative of the second is an e to the 1 over x, e to the 1 over x times negative 1 over x squared. Good. Now, he kind of, did you do that over here? No. All right. The derivative of e to the negative, e to the 1 over x on its own. Derivative, just that one part of e to the 1 over x. Well, the derivative of e to the u is e to the u times du dx, and we have to take the derivative of 1 over x, and it's going to get plopped in there. This is one you want to have memorized. You're going to see this a lot. You could do the quotient rule on this. You could write it as x to the negative 1 and do the power rule. Negative 1 x to the negative 2, which turns into negative 1 over x squared. And that's what goes up there, negative 1 over x squared. So e to the 1 over x times negative 1 over x squared. So Cole, that was not well thought out. I apologize. We get negative e to the 1 over x. That negative 1 stays up top, and the x squared is in the denominator. That's just that part of the derivative. But he knew that is a part of a product rule. First times the derivative of the second. Well, this thing right here is the derivative of the second term. So that gets put into first derivative of the second, and that negative 1 he brought out, plus the second, and then the derivative of the first is just 1. Good with that. He found common denominators, so he could set the numerator equal to 0. We have x e to the 1 over x times negative 1 plus x. How many factors do you see up here? I see an x, I see an e to the 1 over x, and I see a negative 1 plus x. Do you agree? How many factors are there? 3. X times, 1. E to the 1 over x, 2. Negative 1 plus x, 3. So we have to set all factors equal to 0 in the numerator. What happens when you set x equal to 0? X equals 0. Critical point? Kind of. We're going to hold off on that for a second. E to the 1 over x, set that equal to 0. Does e to the 1 over x ever equal 0? Does e to the 1 over x ever equal 0? Do you know how to solve that? We need to be careful. This could take we could spend the whole class period on this problem. Does e to the 1 over x ever equal 0? Question mark. Well, let's solve it. If you don't know graphically, let's solve it. How do you get 1 over x out of the exponent? Log it on down. ln both sides. That allows the 1 over x to come down front. Remember doing this in logarithmic differentiation. This is not logarithmic differentiation. This is just a property of logs. So we get 1 over x times ln e equals ln of 0. Correct? What's ln of e? E to what is e? 1. So 1 over x equals ln of 0. What's the problem? Cool.
There's no exponent that makes e equal 0.
There's no real number that satisfies that. E to what power is 0? No such thing. No such solution. No solution. No critical point from that factor equaling 0. What about when negative 1 plus x equals 0? X equals 1, critical point. Was x equals 0 a critical point? He put it there and then cross it out. Why? 0 wasn't on. Go ahead.
There's an x denominator, which makes it divide by 0.
Yeah, there's no output. It's not on the domain of f, right? Division by 0, not on the domain. Not on the domain. No max or min there. So really, our only critical point was x equals 1. Test it. He didn't draw the number line, but he tested before. He tested 1/2. Did you test after? Looks like
Yeah, there's 2.
Mm-hmm. So here's his disguised number line test. Thank you. He plugged in 1/2. He got a negative. He plugged in 2. He got a.
It's actually the radical e over 2.
Thank you. He got a positive. I don't care what the number is. It's positive, right? The derivative changed from negative before 1 to positive after 1. The derivative changed from negative to positive. There is a local minimum. Minimum. You ever watching that?
No.
Oh. Those are good. Minimum. Thank you. I appreciate that, Cole. That was brave of you. It was a valiant, successful effort.
I'm glad.
So am I. All right. 14. Ooh. Find all points of inflection of x radical 9 minus x squared. Madison, was this the one you said you'd found the second derivative and you thought it looked really ugly?
It was very ugly.
Very ugly.
I just gave up.
Okay. Do we all agree? Product rule. Step 1. F prime of x first times the derivative of the second. Plus the second times 1, the derivative of the first. Be careful. I had to correct a lot of you guys on the last few quizzes. You're doing this, but you're not putting parentheses around terms and it's sloppy, and I would hate for you guys to get in bad habits and have like a professor count off because of just silly stuff like that, or you miss something because you didn't see cancellation. You thought it was subtraction, it's really multiplication. All right, well, I've got f prime of x equaling x over the x squared over the square root of 9 minus x squared in the first term, plus radical 9 minus x squared in the second term. And there's a negative there. Sorry, negative. That negative and the x squared are up top. Everybody with me? This looks like it was a quiz question way back when we did the product rule and chain rule. Do you remember that? Ooh, almost to prepare us. Almost to like practice to get ready for things like this. Interesting. Now, before I take another derivative, I would probably write it as one fraction. Common denominators. Which means I multiply by another factor of radical 9 minus x squared up top. And I end up getting f prime of x is negative x squared plus 9 minus x squared. What's in the numerator? Negative 2x squared plus 9. Everybody with me? Yes. Yes. I know we're feverishly writing this down to correct ourselves, aren't we? Awesome. Step 2, we're doing a test for points of inflection, meaning we're doing the second derivative test, meaning we go straight to the second derivative in step 2. Low. D high. Minus high. D low. All right, and our D low is 1/2. The inside alone. To the negative 1/2 times negative 2x. All over low, low. Let's clean it up a bit. So we have negative 4x radical 9 minus x squared. All right, here we go. We got a 2 and a 1/2. And I'm going to go, yeah, this is ugly, isn't it? I'm going to take, do you guys understand this set of parentheses and this set of parentheses make up our two terms, right? So this negative would not need distributed into both sets of parentheses. There's no addition or subtraction. Do you agree? So any cancellation of negatives can be done in any one of the terms. So I could distribute this negative into those terms. I'm not going to do it. I could make that negative and that negative the positive. That would probably make more sense. All right. So I've got changes to a plus. This and this changes to a plus. We still have that x. So we have a negative 2x squared plus 9 times an x over the square root of 9 minus x squared in that term's denominator. You would never see this on a quiz. All right, so in our numerator, we have negative 4x radical 9 minus x squared, plus we have I'm going to leave this factor. I'm going to write x times negative 2x squared plus 9 over a denominator of the square root of 9 minus x squared all over 9 minus x squared. Are you still with me? Good talk. All right. We have common denominators. Let's make it square root of 9 minus x squared. We have to multiply this times the same thing. We have f double prime is negative 4x times 9 minus x squared plus x times negative 2x squared plus 9 all over the new common denominator of square root of 9 minus x squared all over the square root of, no, just 9 minus x squared, no square root. You ready for this? Distribute. Distribute. Negative 36x plus 4x cubed minus 2x cubed plus 9x all over, don't hate me, 9 minus x squared Did I miss something? Hold on. That I undid one layer too much. Hold on a second. 6x plus 4x squared minus 2x cubed plus 9x over 9 minus x squared to the 3 halves. Okay. Thank you. That's what undid. Yeah, thank you. Here's what I did. I flipped. Keep. Flip. Switch. Keep, change, flip. I flipped and multiplied. I had 1 over 9 minus x squared. Do you agree a 9 minus x squared to the power of 1 times a 9x squared to a 9 minus x squared to the power of 1/2 multiplied to 9 minus x squared to the power of 3/2? Let's say it again. This is 9 minus x squared to the first. This is 9 minus x squared to the 1/2. When this reciprocates and multiplies, I don't know what you guys say, you have the same bases of 9 minus x squared, but you're multiplying them. One has a power of 1, one has a power of 1/2. You multiply the bases, you add their exponents. 1 plus 1/2 is 3/2. Okay, so that's my new denominator. Now all we have to do is clean up that numerator. We're good to go. Would it be beneficial to factor out a GCF? Oh, we can't, other than x, right? Let's clean it up first. We have 4x cubed. We have negative 36x plus 9x, which is negative 27x. Oh, wait, hold on. We have a 4x cubed minus a 2x cubed. That's a 2x cubed. We have a 2x cubed minus 27x over 9 minus x squared to the 3/2. Oh, that's just beautiful. Beautiful. If we factor out a GCF, just of x, we have x times 2x squared minus 27. Very straightforward, I'd say. That's the second derivative. What's step 3? Set it equal to 0, right? Step 3. I don't know where I was going there. All right. Everything's falling apart. X equals 0. It's called a possible point of inflection. And what happens when we set 2x squared minus 27 equal to 0? We get 2x squared equals 27. We get x squared equals 27 halves. Square root, we get x equals plus or minus, don't forget that, the square root of 27 halves. Plus or minus the square root of 27 halves. There's another, actually 2, possible points of inflection. Are you with me? Now, real quick, let's evaluate. We kind of broke one of our rules. What's the domain of this? 9 minus x squared has to be good. 9 minus, well, and 0, right? Greater than or equal to 0? When is the graph of 9 minus x squared above or equal to the x-axis? Between -3 and 3. You agree? Between -3 and 3. The domain of this? Domain? -3 to 3. Is 0 on that domain? Because 0 was a possible point of inflection. Was 0 on that domain? Was the square root of 27 halves. Okay. Here we go. 27 divided by 2 is 13 and a half. Yes? What's the square root of 13 and a half? More than 3 and less than bad. That's my fault. Okay. Positive square root. It doesn't like me doing this problem. Square root of 13 and a half is more than 3. You all agree? More than 3. Okay. How about negative square root of 13 and a half? Less than -3. Are those on the domain of F? So they can't be PIs. They can't be points of inflection. We don't need to test them. We don't need to put them on our number line. Okay? That saved us a little bit of time. 4. Does F double prime of X fail to exist? Well, here's F double prime right here. It's under an even root. Like square root cubed, right? It's a square root cubed. So when you take the square root, you can't have a negative. And you can't cube it if you couldn't take the square root of it, right? So the nice thing about this is the domain matches the original except for at 3 and -3. The 3 and -3 are not on the domain of F double prime. Do you understand that? Please be honest. Do you understand that? Okay. So, yeah, F double prime fails to exist. It doesn't exist at -3 or less or at 3 or more, but we weren't going to test those anyway because they weren't on the domain of F. So I think we're pretty good with that. All right. So step 5 is to test F double prime, which equals X times 2, was it 2x squared minus 27? All over 9 minus x squared to 3 halves. Now we have -3, which is an endpoint, a natural endpoint. We have +3, which is a natural endpoint. And the only test point on our graph was 0. It's not a critical point. What should we call it in the second derivative? It could be a point of inflection. It may not. It's a possible point of inflection. Possible point of inflection. We have F. We have F prime. We have F double prime. What layer do we start with? F double prime. It's called the second derivative test. Second derivative test. Let's plug in a test point. How about -1? And +1. Plug in -1. All we care about is positive or negative. Are you ready? -1 squared times 2. -27. So that's -25, correct? Times a -1, positive. Over a, do I need to plug in -1 for x? It's going to be positive, right? Because guess what? When you square root something, isn't this to the 1/2 and then cubed? When you square root a number, not plus or minus the square root, just the square root, you're going to get a positive. When you cube that, you're going to keep it positive. I don't really need to test the denominator. The numerator is what? Do we get a plus or minus in the numerator? It was -25 times a -1. That is a positive second derivative. And when we plug in 1, we're going to get 2 minus 27, which is -25, times a +1 is a negative after. All right. Now the point, that was really messy. That was a lot of ugly algebra. And again, it was the algebra that was the tough part. I guess the chain rule was kind of tough there. But here, if you zoned out, if you were daydreaming, you need to listen to this point. To this point. Cool.
Why didn't they test the denominator again?
Because it's always positive.
Couldn't it be plus or minus in the square root?
It's not plus or minus. It's only plus or minus when you're uncovering it. And this is worth talking about again. Are you ready? X squared. I'm going to make this a nicer number. Ready? X squared. I'm changing the number. X squared equals 9. What could X be? Could it be 3? Is 3 squared 9? Could X be -3? Is -3 squared 9? Yes. So when you uncover that X, you have to allow for the plus or minus. But if I said, that's not really the question I wanted. I want it to be a function. I don't want it to be 3 and -3. I want to keep it a function. I'm not going to give it to you that way. I'm going to say X equals the square root of 9. What's the square root of 9? 3. If I wanted it to be plus or minus, the author of the problem would have had to have put a plus or minus out in front of the square root of 9. Because the square root of 9 is 3. But if I say what squared gives you 9? 3 and -3. Do you hear the difference? Okay. So was there a plus or minus in front of the square root? No. So we only assume it's the positive portion. All right. Make me proud. If f double prime is negative on an interval, your f primes must be.
You said negative.
Did I say negative?
Yeah.
That was embarrassing. I apologize. do that whole complicated calc problem, and I can't keep my positive and negative straight. Take 2. If f double prime is positive, f primes are increasing. And if your f primes are increasing, F must be concave up.
Concave up.
What's that? Oh, it's concave?
No, down.
Is he? Where'd you get suspended? I was confident. All right. Could F be concave up and increasing? By the way, do we know if F is increasing or decreasing? No, we just know that it's concave up. Could F be concave up and increasing? Yeah, I think we all see that. Am I doing that the right way? Yeah, to the right. I have to do everything backwards. Okay. Could F be concave up and increasing? Yeah. Could F be concave up and decreasing? See it? So we don't know whether F is going up or down. We just know it's concavity. All right? Moving on. If F double prime is negative, your F primes are, and F must be concave down. So this test is not a is F going up or down. It's a curvature test. It's how is F curving. Okay, and I'm going to introduce a couple phrases that may be new to you. I don't know. I forget if you guys have heard this before or not. Ready? And then we'll wrap up this problem. F, here's F. I'm graphing F. F is increasing at an increasing rate. Have you heard that expression? Okay, good. F is increasing at a decreasing rate. Okay, now that you've learned this, what are you really saying as you say that expression? F is increasing and the derivatives are decreasing. Oh, so instead of the word rate, we're really talking about derivative. F is increasing with its derivative decreasing. Rate of change, derivative. Oh, okay, makes sense. F is increasing and its derivative is increasing. Do you see it? All right. F is decreasing at an increasing rate. Why? Because its slopes are becoming, well, the slopes are increasing. They're becoming less negative, right? F is decreasing at a decreasing rate. Does that make sense to you? Excellent. Wrap up the problem. We were asked about points of inflection. Guess what? Congratulations, x equals 0. You graduated. You're now an actual point of inflection. So a point of inflection at 0, comma, where should we plug in 0 to find out its coordinate? Way back. Oh, that was exhausting. Scrolling for days. They see me scrolling. They hate me. All right. What's the point? 0, comma, 0. Oh, that was boring. 0, 0. 0, 0. Should we graph it? Oh, what'd you guys do today? Oh, one problem. Quality. This, like, honestly, this is, like, I have flashbacks to college calculus where, like, you do, like, 3 problems and it was, like, 3 pages. Like, I had a proof one time. It was called, what a terrible course name. It was so misleading. It's called Elementary Foundations of Algebra. Oh, it's an easy class. Never had a number in the whole book. Like, it was all letters and set theory and there's elements of this sets and abelian groups. And I was like, oh my gosh, I have no idea what I'm talking about.
Why do all the math classes call it elementary?
Right. It's like, elementary topology. Sounds easy. Nope. It's the math of tying knots and whether a knot can be untied and how many like writing equations for the combinations of untying possibilities.
Did you take that class?
Yeah. Discrete math and combinatorics. I think I told you guys about my senior year in college. Like 4 senior math classes, and I tutored at the tutoring and testing center, and then like I was student teaching, and it was like math was my life, like all day. And I would go home and do homework. Got old.
One of your math teachers.
I am. Help me out. The original x times the square root of 9 minus x squared, right? Ooh, you are who we thought you were. You exist between -3 and 3. You're concave up on the interval from -3 to 0. You're concave down on the interval from 0 to 3. Do you agree? I feel good about that problem. All right. In all fairness, this is AP Calc. You need to see problems like that. I know it's ugly. I don't know if one person in the room got that with correct math. Did you? Did anyone in the room get it? Lizzie got it? No. Cole, you got it? With correct math?
My second derivative was, I had 3x squared instead of 2x squared.
Okay.
So not really.
Close.
But I had to.
Yeah.
Okay, gotcha. Well done. Here's what I will say: it's good experience to have to do that. I urge you to go back through that and try to see the algebra. It gets ugly, but it's a good problem. So what's expected of you? Well, honestly, in all honesty, problems more like this will be a typical problem. Okay. You should be able, if you can't do this, we need to talk. I'm not trying to say that out of being mean. Just as a checkpoint, you should say, I can do this, or no, I can't, and I need to talk. Like, we need to talk. Because this is one of the typical ones that you would probably see on a quiz. One that's cubic or whatever. All right. How many points of inflection could a cubic have? Most, at most. Well, what's that question disguised at? Man, I did a lot of disguises. Thank you. And I don't realize how much I did it. It's a problem. No? Okay. Well, isn't it really asking how many times can the second derivative equal 0? Okay, so cubic. First derivative is going to be quadratic, power of 2. Second derivative is going to be linear, and how many times does a linear function equal 0? At most 1, right? Do you get it? So like, remember the rational roots theorem? You guys ever do the rational roots theorem? A quadratic can have up to 2 real roots. Could have 2 imaginary. Remember that? A cubic? Well, isn't this really asking how many times does its derivative, second derivative equal 0? Kind of the same thing. So when you do a problem like this, you kind of know what could happen. You kind of know where you're going. You just have to show the correct math, correct possible points of inflection, and then the correct test. So, homework for tonight. I think it was actually on the worksheet that I'm going to give you guys. Hey guys, real quick. Actually, 2 things. One, on this worksheet, you're going to do, if you read off of the Google slide, I'm going to change it because we didn't get as far as I was hoping today. I'm going to have you do number 1, 4, 1, 4, 6, and I want you to try 7 now. Okay? 1, 4, 6, and 7. 1, 4, 6, and 7. Did everyone get one? Last thing, Madison asked, would you ever see a question like number 14 on the AP test? Quick answer, no. Reason? They're not testing your algebra skills, they're testing your calculus skills. So they may like give you a kickstart and get you halfway into the problem and say how many points of inflection could this graph have. So you don't have to muddle all through the algebra. You can just go straight to the second derivative. Or I've seen it where they'll give you like a table, f prime, f double prime with x values, and they'll say f double prime of 2 is 0, and then you look on their table, and before 0, f double prime is positive, and after it was negative. How many points of inflection could f have?
Yeah.
Just from a table. Yeah, good question. You're welcome.